Here's another type of reaction. So we just did a hydration of aldehydes or ketones. This is called a cyanohydrin formation. The one reaction I want you to really worry about and think about is this one. And what happens here. So the first step, let's talk about the cyanohydrin formation. So in this case, you have a ketone or aldehyde, and you have this KCN and then HCN. So let's put our charges in. CN minus, right, cyanide. This is a way to add one carbon, right? Because cyanide has one carbon. Is this acidic or basic conditions? This is definitely basic conditions. You have a carbon with a negative charge, so it's basic conditions. So the first step is going to be adding in. Make a tetrahedral intermediate. And at this point, this CN is actually a catalyst. The cyanide is actually a catalyst. And you regenerate that by deprotonating the hydrogen cyanide. Right? So a protonation, like we always see at the second step for these. And we've made what they call a cyanohydrin. So that's what this is. This is a cyanohydrin. So now what I want us to be able to do is, here's the cyanohydrin. This is mimicking up here. I want you to take the cyanohydrin in acidic conditions with water. I want this nitrile to somehow turn into a carboxylic acid. So right, just looking at this, how would this have to happen? What's the first step going to be? All right, the first step, we're in acidic conditions. What should the first step be? Protonation. This nitrogen has a lone pair. Protonate that nitrogen. Have water react with this carbon, because that's where this carbon is right here. You're probably going to have to add water how many times? There's 2 oxygens. You have to add water how many times? Twice. Water is a solvent, there's a lot of it. H plus is a catalyst. So let's try to see if we can do that. I'm going to put you in groups and see if we can work through that. All right. So we've done hydrations. I showed you how to do a cyanohydrin. I've tasked you with thinking about ways to turn that nitrile in acidic conditions with water to a carboxylic acid. We'll look at that again. Next thing I want to cover is acetals and hemiacetals. And again, the reason we do these is a way to actually make an aldehyde or a ketone less reactive. We consider these kind of like protecting groups. Think of it like a mask. You're putting a mask on. So this carbon, right, we know this carbon is pretty electrophilic. But once you do this, make these acetals, it actually makes it less reactive. So it's like a mask. They call them protecting groups in chemistry. We change its reactivity, make it less reactive. So what I want you to do now is practice in acidic conditions, right? Acidic conditions, and you have a lot of this alcohol, 2 equivalents of this alcohol around. Can you draw the acetal formation here for this one? Okay, so we're going to work on taking an aldehyde and turning it into an acetal, right? And why do we do this? We do this to make the carbon of the carbonyl group less reactive, right? These are called protecting groups. Think of it like these are fun because these are all internal. The diols on the same, the alcohols on the same one, so it looks like a mask. So it's like hiding the functionality to make it less reactive. In acidic conditions, of course, the first step will be protonation. So it's H3O plus up here, but you can just draw that as H plus. H plus, so it's just like hydration. We did hydrations. It's similar to hydrations, but now we're adding alcohols instead of water. Protonation makes the carbon of the carbonyl group that much more reactive. In this case, the alcohol, this ethanol, is going to come in and add in addition. We're going to form a tetrahedral intermediate. No skipping steps. No skipping steps. Balancing charges. We get to this. Right now, again, tetrahedral intermediate. This is actually the best leaving group. But we know we're actually losing water in these. So to balance this equation out, we should have drawn water. We can do a proton transfer. Right? We can move this hydrogen to this oxygen. to make that a better leaving group, right? What's the point of all these proton transfers? The point of the proton transfers, more often than not, is to turn something into a better leaving group, right? That we know we need to lose. So that turns this into a better leaving group. Tetrahedral intermediate. Lone pairs come down. We do that elimination. So following that elimination, right, we get this plus charged oxygen. Right, it has 3 bonds. Looks like it's reactive. Another one of those ethanols comes in. Right, notice it said 2 equivalences here. A lot of times it'll just be the solvent. If you see something that's a solvent, just assume there's a lot of it. Solvent means there's a lot of it. Lots of equivalences. Activated carbon to carbonyl reactive. We do another addition, another alcohol adds in, and we knew that though because we looked at the start of the product, we knew we needed to add 2 of these. So we had to get there. Do that addition. Balance our charge. And of course, this is acid catalyzed. I'll always be very careful about adding that in. And the last step would be just regenerating that catalyst so that H falls off and we get our product. And it's basically the same exact mechanism for the other one, just with a ketone. And the only difference in that one is the protecting group you're putting on, the alcohols are on the same molecule.